Our next speaker, this is going to be terrific. In October of last year, Boaz Almog and his colleagues in the superconductivity lab at Tel Aviv University demonstrated how a superconductor disk can be trapped in a surrounding magnetic field. And this is a phenomenon called quantum levitation. And now we get to see it as well. So, ladies and gentlemen, all the way from Tel Aviv, Dr. Boaz Almog.
Hi. First of all, I want to thank the organizer for inviting me here. It's been a great pleasure. And what I'm going to show you today is actually the result of many years of research, actually 3 generations. And this is our superconductivity group, our professor Deutscher and my colleague Michel Azulay. So you're going to really see the result of many years of hard work. And let me start by quoting a famous science fiction novelist, Arthur C. Clarke, who said that any sufficiently advanced technology is indistinguishable from magic. And let me rephrase that and say that any sufficiently advanced science is indistinguishable from magic. And let me show you some magic. Can you give me? I forgot something very small. Excuse me. No, I needed tweezers. Sorry. I need some props. I'm a physicist, so I'm sorry for that. So I have here a very cold superconductor, a disk, which is a superconductor. And when I put this superconductor, I can't touch it with my fingers. That's why I needed the tweezers. And it just levitates. I don't know if you can see this, but maybe you could help them. It just levitates in free air. Okay? Now, there's no strings, nothing. It just levitates. Now, this is actually not magic. This is actually quantum physics. And I know I'm not going to get inside quantum physics. It's quite complicated and maybe boring, but in order to understand this new physics, this new nature, we need to develop a new intuition, because this is nothing like we know in our everyday life. So I'm going to give you a little bit of this new intuition, so you won't think it's magic. So superconductivity is actually quite an old phenomenon. It was discovered in 1911 by the Dutch physicist Kamerlingh Onnas. And if you look at the definition of superconductivity in Wikipedia, which is not always reliable, but in this case it's okay, superconductivity is a phenomenon of exactly zero electrical resistance and expulsion of magnetic fields which occur in certain material. So, sounds complicated, but let's try to understand that. What is electrical resistance? So, in every conductor, there are these current-carrying particles, the electrons. And these electrons, they collide with the atoms, they collide with each other. And they lose a certain amount of their energy. And we all know that because, they dissipate their energy into heat. And in our everyday life, there is always some friction. In everything we do, we lose a certain amount of energy. But not here. In superconductor, they do not lose any of their energy. It's a quantum state of the matter. Now, it turns out that it's not the only thing. And as another physicist, Meissner, discovered, superconductors and magnetic fields have a very unique relationship. And it turns out that superconductors do not like magnetic fields. They try to expel the magnetic field from the inside. And how do they do that? Simply by driving currents inside, because currents do not cost any energy. They are superconductors. So they will create small electromagnets which will cancel the external field. I'm sorry for the technicality. It will soon be over, I promise. Now, the combination of both effects is a superconductor. Now, do you understand the levitation yet? No. So that's not enough. there's only one thing left. And the fact that life isn't perfect, and we know that life isn't perfect, and it's good for us because sometimes magnetic field lines, strands of magnetic field remain inside this superconductor. And because this is a quantum physical effect, quantum effect, the magnetic field behave like quantum particles, like quantum object. You can see here in this film taken by a Japanese scientist how this flux line, how these magnetic field lines, they flow discretely inside the material. Remember, this is magnetic field lines, and they behave like particles because this is quantum physics. And if you look closely at the film, you see that some of these fluxons, some of these flux lines are pins. They do not move. And the reason for that is that the superconductor doesn't like the magnetic field lines moving around. So what it actually does, it locks them in place. And by doing that, it locks itself. Look, this is the disk before we cooled it. The magnetic field lines just go through and through. And when we cool it, some of it is expelled. This is the Meissner. But some of it remain, and the superconductor locks these magnetic field lines, invisible lines. And what actually happens is quantum locking, quantum levitation. And let me show you how it really looks like. So again, I have this superconducting disk. I have to cool it with liquid nitrogen because all these nice properties only happen below a certain temperature. That's the downside, for now at least, until we find new materials. So I'm going to take this superconductor, and now I can lock it. I can force the magnetic field lines inside the material, and it will stay locked. I can rearrange the fluxon. It will stay locked like this, or like this. And it is three-dimensional locking. This is not repulsion. It's not like two magnets. No, nothing like that. Because if I turn this upside down, it just stays. Okay? Forget everything you know about classical physics. This is different. Okay? That's my point to you. Forget everything. It's difficult, right? So, now that we understand that, yeah, we understand, that quantum locking and quantum levitation is just the superconductor trying to keep everything as it is, to keep the magnetic field as it is, you wouldn't be surprised to find that if I take this circular magnet, these are two circular magnets, the superconductor will have no problem circulating, moving around the axis of symmetry, because as long as it's rotating, nothing changes. It's symmetric. So if I'm going to take this superconductor, I'm going to lock it inside. Now I get frictionless motion, and it's still levitating, and I can turn it upside down, I can move it, and it rotates without any friction besides the friction of air, of course. So the basis of any quantum levitation application, at least that I think of, in the future, would be the frictionless motion that we get here. So before I go on and show you more about the levitation itself, let me tell you a little bit about the material, the superconductor itself. Now, I won't go into details, but there is something very important you should know about this. And mainly that most of this disk, you see this is a few millimeter thick disk, most of it is non-superconducting. It's just substrate and thermal cover and so on. And the actual superconductor is only half a micron thick, less than the thickness of a hair, a human hair. And this half a micron thick superconductor levitates more than 70,000 times its own weight. It's a remarkable effect. It's a very strong effect. Why? Because it's quantum physics. It's a new set of intuition. Now, I just want to give you an impression of how we do it, how we get this superconductor. Well, it's quite complicated because the superconductor needs to be very high quality and have specific properties. But basically what we do is very simple. We take this sapphire disk, and you can see the glow behind the disk. These are just atoms that we throw on the sapphire. It's quite simple. The atoms fall on the sapphire, and they just grow if you have the right recipe. I told you about quantum levitation. Let's see how it works. So I have here a different configuration, a different set of magnets. I put on a rail in which the magnetic field is the same along this rail. So the superconductor will move without any friction on this rail. Let's see if it works. I'm going to cool it a little bit more. And then I'm going to lock it on top of this rail. And you see, it just levitates. If I had a 20 meters long rail, it would just go without any friction. You see, the amount of energy I need to move this disk is minimal because there's no friction. If I take this circular rail, you see these are just two circles of magnets. And if I take the disk and put this on the rail, you'll see that it immediately starts moving. I give it a little push, and that's enough. It will keep rotating until it warms up. So there's no friction at all. Now, I can do the same thing on this rail, but upside down, because again, this is not magnetic repulsion. So if I take this disk and pin it below the rail, it will just move below the rail. Again, forget everything you know. This is not classical physics. You forgot? Okay. So this is quantum levitation and quantum locking in space, right? So I'm going to let it roll here a little bit longer, and I'm going to tell you about the applications of superconductors. So first of all, in general, superconductors, as I said, they conduct electricity without any friction, without any dissipation. So the first thing that comes to mind is making cables, power cables, to transfer energy, to transfer electricity. And people are trying to do that. For example, on the right here, you see a cable. This was just published last year. It's a group. They're trying to make a superconducting cable. And on the left here, you see what we're trying to do in Tel Aviv University. We're trying to take sapphire fibers, similar to optical fibers, and we try to coat them with a superconductor. And that's why you'll have a superconducting wires. And what can you do with superconducting wires besides power stations, besides driving electricity, which is important, very important? You could make strong magnets, for example. And why do we need magnets? For example, for MRI machines. You know that every MRI machine has a superconductor in it. But the problem is that the superconductors currently inside MRI machines need liquid helium, which is much more expensive. So the whole big MRI machine that you see is just a liquid helium liquefier. So if you could make an MRI machine with this new type of superconductors, they would be smaller and cheaper. And this one is actually, I found this online. There's a company that already make MRI machines, small MRI machines. And of course, if you would have superconducting wires, you would have better particle accelerators, and you could store energy, again, because there is no resistance. And what about quantum levitation? So the basic idea is that you have frictionless motion. And if you have frictionless motion, you can make better motors, much more stronger motors, and much more efficient generators. And you can even store mechanical energy. Remember how it rotated without any friction? You can store mechanical energy that way. And these are all under development all around the world. And what about levitating trains? So, of course, this is the immediate application, and there are many groups. For example, you see here a prototype from China, and there is a prototype in Brazil. And you can see a scheme of how, if I press here, you can see a scheme of how to levitate an entire train so it will move without any friction. So there are many, many applications for quantum levitation. And you can even take this concept a step farther. And this is the future we're talking about. And we already eliminated the friction with the rail, right? So we're just left with the friction with air. So why not take the air out? And why not make trains that move inside evacuated tubes? This way we'll have much more efficient transportation, much cheaper. Imagine you can travel between Europe to the US for $100. That's amazing. You can see the concept here. And I want to leave you with one more thing. And I want to show you a demonstration which will summarize all the properties of quantum levitation, I think, in my opinion. And what I'm going to do, I'm going to first cool another disk. So bear with me. Remember, liquid nitrogen is cheap. It's cheaper than milk. So cooling is no problem. There are other problems, for sure, but cooling is not a problem. And you can see it's very easy to handle. So I'm going to take another disk, and I'm going to lock it above the rail at a certain position, and I'm just going to let it flow without any friction. And then I'm going to take another disk, and I'm going to lock it at a different configuration, and then I'm going to let them spin. Thank you. I can play with this for hours, so.
Are you done? Are you?
I can play. I can keep on playing with it. I have no problem.
No, that's terrific. We'll talk while this is going on. So, so I know the problem here is warming, right? But how long would this last if you had a temperature-controlled room?
It depends on the isolation. You know, if you're making a large, or at least 1 meter train, you could make it last 4 hours for a day. You have specific special cryostat that isolate the liquid nitrogen, and then you could just last 4 hours. It's like refueling the train, for example.
And so let me just get it straight what it would take to build a perpetual motion machine, and if such a thing is even possible. Because I'm always told it's impossible.
It's not a perpetual motion because you have to cool it. And in this case, we have the friction with air. So you have to give it a nudge once in a while, so it will overcome this friction.
But in your evacuated tube?
So in the evacuated tube, in principle, yes, it will keep on going forever. Yeah.
So how cheap would it be to actually run? It would be free to run it, right? Once you have the evacuated tube.
No, you still need the cost of the acceleration. You have to get to a certain speed. Once you get to that speed, it's almost energy free. You keep on moving in that speed, and then you have to decelerate, and that's it. It will be much, much cheaper than currently rails and airplanes, and much more energy efficient. Yeah, for sure.
Yeah. And what's next? What's the new thing coming out of Tel Aviv next?
I hope that we'll have fibers soon, in a year or two. And once you have wires, superconducting wires, you can actually do anything. You can do electronics. You can transfer currents in them, electromagnets. Anything is possible. And the previous talker just mentioned in a brief words about building with the nanotubes an elevator to space. How would this elevator go, it will levitate with quantum levitation because there's no friction. So you have to combine technologies. That's it.
Well, the next generation is very lucky. Thank you so much for being here.
Thank you.